In this video, we will clarify what makes a hypothesis testing one-tailed or two-tailed. We will also define what a p-value is and see its connection with hypothesis testing. So take note that the object that receives the action in hypothesis testing, whether to reject it or accept it, is the null hypothesis. Remember also how these decisions may be prone to errors, such that we may reject our null hypothesis even if it's true. We call this a type 1 error, or alpha. And we may accept the null hypothesis even if the alternative hypothesis is true. We call this type 2 error, or beta. But our aim in hypothesis testing is to make these probability for errors as small as possible. Making alpha small involves rejecting the null hypothesis less often, and making beta small involves accepting the null hypothesis less often. So the custom way to do this is to fix alpha first at our desired level and to make our method stringent to avoid bias as to maximize the power of the test, also known as minimize beta. So for example, if we want to test the null hypothesis that rinsing our hands with disinfectant X has no effect at all in reducing our chance of getting the flu, so we might arrive first at a null hypothesis that might be written this way. We might want to measure this by getting 3 samplings of 30 individuals who we require to rinse their hands with disinfectant X regularly. We then compare the incidence of flu in these 30 individuals with the general population, okay, in a given time span. We can then formulate an alternative hypothesis that there will be less incidence of flu among the individuals who used disinfectant X than the general population. So our alternative hypothesis might look something like this. So we have our null hypothesis and then our alternative hypothesis. Okay, so mu being our test subjects and mu sub 0 being the general population. Next, we have to decide what our significance level, or alpha, be. What chance can we give for type 1 error? Okay, so usually alpha is set to 5% or 0.05. So there is a 5% chance of rejecting our null hypothesis. There's a 5% chance, even if it's true. Put in another way, this is the time we decide on the confidence interval for our population mean. So we have a population mean distribution. Okay, so we've learned from estimation about confidence interval. So here we have our population mean. And because we have decided to set alpha at 5%, the confidence interval that we have chosen is going to be 95%. Okay, so everything here in the middle. Okay, but because we are based on our null hypothesis, we are saying that the mean from our test samples will be lesser, okay, or the incidence of flu will be lesser than the incidence in the population. We are going to keep our alpha in this side. So this one is our alpha. of 5%. And everything above that is the 95% confidence interval. So the question now is, how do we test the null hypothesis? If the sample mean or average of the incidence of flu in the samples, meaning to say this mu here, okay, that we ask to use disinfectant X is sufficiently lower than that of the general population, mu sub 0, then we reject our null hypothesis. Meaning to say, if this mu here happens to be somewhere in this alpha, okay, then we will be rejecting our null hypothesis. Okay? Because this is our confidence interval for mu sub 0. So if our mu from our samples is in this alpha, meaning to say outside of that confidence interval, then we will be rejecting our null hypothesis. If the same sample, if the sample mean or average of incidence of flu from the samples, if this one is within the confidence interval of mu sub 0, then we accept our null hypothesis that using disinfectant X has no effect. Okay? So again, if our mu from our sample, okay, why mu from sample? Because your sample mean estimates mu. Okay? If our mu from the sample is way below this, then we can accept our alternative and reject our null hypothesis. Meaning to say that there is significantly lower cases of flu in our test samples. But if our mu from our sample is within this confidence interval, meaning to say that there is really no difference between the general population's incidence of flu and our sample's incidence of flu. Okay? So that's how alpha might work here. Okay? We set alpha first so that we can have a confidence interval. So, where is the control for the type 2 error here? This happens, or the control happens, when we are strict with our procedures. Say, when we make sure that everyone who participated as our sample for disinfectant X really rinsed their hands regularly and properly with disinfectant X. So the control for the type 2 error happens with how stringent you are in your procedures, how strict you are. This allows us to be sure that the results will really go against our null hypothesis if ever disinfectant X is indeed effective. So here we have our, what we call as our acceptance and rejection region. Okay, so if I'm going to illustrate the T distribution that I drew a while ago, okay, and then this is our 95% confidence interval, and then this is our alpha, which is 0.05. The acceptance region is the range of values for our sample mean for which our null hypothesis is accepted. Okay? So meaning to say, if our sample mean or our mu or our x bar, because this is mu sub 0, is within this 95% confidence interval, then we accept HO. So therefore, this portion here is also our acceptance region. Okay? So again, this portion. Now, the rejection region is the range of values for our sample mean for which we will reject our null hypothesis. So if our sample mean or mu as estimated by our sample mean is already out of bounds of the confidence interval, it's already in our alpha region here, then we have to reject the null hypothesis and say that the use of disinfectant X actually greatly reduced the risk of flu in our test samples. So these are the acceptance and rejection regions. Which brings us now to what we call as the one-tailed test. Okay, so this illustration that I have here, I know it's overlapping over the text, okay, shows us that alpha is towards the left. So this portion here that I'm shading, okay, and everything else to the right, including the rightmost portion here, are part of the confidence interval. So if alpha happens to be on one side of our t distribution, like the one here, or maybe if I have another t distribution, our alpha is placed somewhere here to the rightmost part, then we are actually performing what we call as a one-tailed test. Okay? So, in a one-tailed test, it's a test in which the values of the parameter being studied, in this case mu, under the alternative hypothesis is allowed to be either greater than, like here, okay, or less than, like this one, the values of the parameter under the null hypothesis, but not both. So it can just be an or, less than or greater than. Okay, so that's a one-tailed test. So in a one-tailed t-test, okay, the critical value is defined as the t with n minus 1 degrees of freedom and then alpha percentile. Okay, so this is a less than, okay, alternative mean is less than the null mean. So meaning to say our shaded region is somewhere here. Okay, and then this portion here, this borderline here, is our t sub n minus 1 at alpha percentile. Okay, so in our example a while ago, this alpha percentile was the 5% percentile. So this is our critical value. Meaning to say, if our value for our sample mean is beyond this critical value, then we will be rejecting our null hypothesis. But if the sample mean is within this critical value, then we will be accepting our null hypothesis. Now the opposite will be true if your hypothesis now will be the greater than symbol. Okay, so this is still one-tailed. Okay, but this time our critical value, okay, will already be in t n minus 1 degree of freedom, but the percentile becomes 1 minus alpha percentile, or this border here. Okay, so meaning to say, if our sample mean goes over that border, then we have to accept the null the alternative hypothesis and reject the null hypothesis. But if our sample mean is below that critical value, somewhere here perhaps, then we have to accept our null hypothesis, okay, because there is no enough evidence that it should be rejected. So these are all one-tailed tests. So let's try with this particular problem. Okay, so this was the same problem with the women under low socioeconomic status. They deliver babies that are lower than normal ang birth weight. So that's our hypothesis. Our hypothesis, our alternative hypothesis is the babies that they deliver are lower in birth weight than normal. So to test this hypothesis, we obtained 100 samples, okay, from an hospital in the low socioeconomic status area. And then we found out that the mean birth weight in our sample is 115 ounces with a standard deviation of 24 ounces. And we know from the general population that the mean birth weight is 120 ounces. Okay, so in order to perform here our hypothesis testing, which is a one-tailed test. Why one-tailed? Because in our alternative hypothesis, we said that the mothers in these SES areas deliver babies that are lower in normal, okay, in terms of birth weight. There is a direction, meaning to say the hypothesis here is mu less than mu sub 0. That is our alternative hypothesis. So this is one-tailed. So in order to perform this one-tailed test, we need to convert first these into t values. This 115, which we'll put here. Okay, so that sample mean is 115 minus the population mean, which is this 120 ounces, divided by the standard deviation from our sample, which is 24, and the ratio of that and our number of samples, which is 100, so the square root of 100. So if you have your calculators and then you subtract 120 from 15 and divide that with the quotient of the standard deviation and the square root of n, then you will arrive at the t value of negative 2.08. Okay, now take note, this is at alpha 0.05. Okay, so what do we need to do next after we know the t value? You can use the t table, but you know, the t table, I don't think it shows us a sample of 100 or a degree of freedom of 99. So instead, we can use Microsoft Excel to find the value of this. Okay, so in order to find the value, we use t dot inverse, that formula. Okay, and the value of t at 99 degree of freedom and 0.05 percentile is actually negative 1.66. Okay, and take note that our sample mean here as converted to a t-score is negative 2.08, and that's exactly less than what the t value is of 99 degree of freedom and 0.05 percentile, which is negative 1.66. Therefore, what can we say here? We will be rejecting our null hypothesis at significance level of 0.05. Okay, meaning to say, we will accept this because look at this, they're the same, right? Okay. So, what about at alpha that's 0.01? Will the results differ? Okay, remember that as the alpha decreases, okay, let me draw the alpha or the confidence interval. Well, when alpha is 0.05, if we had a confidence interval here, it would have been shorter. Okay? But when alpha has been reduced to 0.01, the confidence interval becomes wider. Okay, now look at this. This is now a wider confidence interval as compared to the red one here. Why? Because we decreased our alpha from 0.05 to 0.01. So what happens if we now considered alpha that's 0.01? Okay, so again, we use Microsoft Excel, okay, to compute for our t or critical value when our alpha is 0.01. So you simply replace this with 0.01, and that will give you a critical value of negative 2.36. And our sample mean here, instead of being lesser than that, is greater than that. Therefore, at 0.01 significance level, we will be accepting our null hypothesis that there is no difference, okay, between the birth weights of the women in the low socioeconomic status area and the general population at large. Okay? So take note, simply by changing our significance levels, our decisions have somehow shifted from reject null hypothesis now to accept null hypothesis. So we will deal with that particular problem later on. So this time we have a two-tailed test. Okay? So in a two-tailed test, instead of just stating your alternative as less than or greater than the population mean, what you have is something like this, not equal to the population mean. Okay? So when your alternative hypothesis is stated this way, then you are to do a two-tailed test. Meaning to say, if you have your t distribution here, if you have an alpha of 0.05, then you would have to divide that into alpha over 2, 0.025, and in both sides of your t distribution, you will be shading the rejection regions pertaining to that 0.025. Meaning to say, if we add both of these, they will still total to 0.05, your original alpha. Okay, so this is now two-tailed test. So I just modified here our example a while ago, but the operational word here is in the alternative hypothesis that mothers with low socioeconomic status deliver babies whose birth weights are not normal. Okay? So take note, my word here now is not normal, instead of saying lesser than the normal. So this is now a two-tailed test. So if we are still going to use alpha at 0.05 here, then we have to divide that into 2. Okay? So as usual, we get our t statistics, doesn't change, still the same, negative 2.08. Okay? But this time, when we try to get the critical value in Excel, okay, instead of just putting in 0.05, we will have to divide that and input 0.025. Okay? And the result will be this. This is our critical value in Excel. Okay? So meaning to say, if we draw here a t distribution, and then here are our rejection regions. Okay? We see here that our t statistic, the absolute value of that, which is 2.08, is greater than the absolute value of 1.98. Meaning to say, if this is 1.98, okay, if this line here is 1.98, this 2.08 is way beyond that, somewhere here. That could be your 2.08. And that means the decision is still to reject your null hypothesis at significance level of 0.05. But what about at significance level of 0.01? So again, using Microsoft Excel, we input this using the formula T dot inverse. And then instead of 0.05 divided by 2 here, we have 0.01 divided by 2. And let's see what the result will be. That's a negative 2.63. And if we do absolute values for these, we see here that that is greater than our t statistic here. So meaning to say our t statistic at 0.01 significance level is somewhere here in the acceptance region, while our critical region here, or critical value, is way above that one. So meaning to say we accept our null hypothesis at 0.01 significance level for a two-tailed test. So you see, one-tailed or two-tailed, this particular problem, the decisions are the same. Accept in 0.01 significance level and reject at 0.05 significance level, which leads us back to the question. So it doesn't really matter if we're testing the hypothesis. All we need to do is adjust our alpha, and depending on the alpha, we may either accept or reject. Well, technically, that's true. In order to avoid that, we have what we call the p-value. Okay? So, when defining the p-value, I think this is the best definition. It is the probability under the null hypothesis of obtaining a test statistic as extreme or more extreme than what you got in your test statistic. Okay? And that's your p-value. Okay, so let's look at our examples from a while ago. Now, before we go there, this is the formula to find p-value in Microsoft Excel. T dot distribution, and then we input our t statistic, and then the degree of freedom, and then we simply choose cumulative. So back to this. If we are to get the p-value here, okay, if I'm going to draw, let me draw first the t distribution. My writing material is not working quite well. Anyway, okay, if we are going to get the p-value here using Microsoft Excel, that p-value is going to be 0.02. Now, what does that mean? That means that if we have a t distribution here, okay, and our t value as we solved is negative 2.08, so that's somewhere here. So this is negative 2.08, okay, and then we can shade this one. This exact shaded region bounded by negative 2.08, this one is the p-value. Okay, so you might want to have a play of ideas here. You can actually try, okay, and prove that this is true by inputting 0.02 here and then degree of freedom 99. You are going to arrive at the answer, your t inverse will be negative 2.08. Because that is exactly what the p-value is, okay? The one that's bounded by your negative 2.08 to the left. That's the 0.02. Okay? So that's the probability of, again, getting negative 2.08 or lower. Right? Okay, that's the probability. That's the p-value here. Okay? If we are going to have the two-tailed test, then this is how you're going to get your p-value. T dot dist dot 2t. Okay? And if we're going to get the p-value here, it's going to be 0.04, meaning to say that if we have this two-tailed shading here of our t-distribution, okay, of 99 degrees of freedom, this negative 2.08, which I'm going to draw here, negative 2.08, okay, this value here is a 0.04. Okay, so that's the probability of this is the probability of getting a value that's equal to negative 2.08 or lower or higher. Okay, now, what do the p-values tell us? Okay, you don't have to worry later on solving things manually, especially in the final project, because Microsoft Excel will just give you your p-value right away without even solving it. Okay, if the p-value is greater than 0.01 but less than 0.05, like in our examples a while ago, then the results are significant. Okay? If the p-value is greater than 0.001 and less than 0.01, then the results are highly significant. So the lower the p-value, the more significant your result will be. And we are talking statistically significant. Okay? If the p-value is lesser than 0.001, then your results are very highly statistically significant. And if the p-value is greater than 0.05, then your results are not statistically significant. Okay? So, instead of just focusing on alpha all the time, you may actually move your attention into the p-value of your hypothesis test. And that will tell you how significant your results are. So in the next video, I will be demonstrating in Microsoft Excel how to do a 2-sample and a 1-sample t-test.